Okay, let's figure out which one of these Bear River watersheds has the highest density of polylines per area. So what we want to know is which watershed has the highest density of streamline. So to do density, it's going to be the length divided by the area of the watershed, because we're trying to normalize against really big watersheds having an obvious longer polyline length. So we're looking for a density. So to do that, hydrologic features like a watershed and these stream polylines are going to probably be related to each other logically, so that at the drainage or the output, I would expect the polyline to be cut at the watershed boundary, like you see here. But if you were working with roads and watersheds, for example, they aren't necessarily, physically related to each other logically. And so I would absolutely always run a clip or an intersect to make sure that the lines that cross the boundary are cut. And then you absolutely have to recalculate the length of these, because that won't automatically update. If this segment had crossed, this new segment, shorter segment, would have the original length, and this little segment would have the original longer length in the attribute table. So you have to recalculate those. So let's go ahead and run the clip, even though I'm sure that these are related to each other and cut at the boundary, but always safe, not sorry. Okay, so we're going to run just a basic clip. My clip feature is the watershed boundaries, so my input features are the NHD polylines, and of course I'm going to name it and put it someplace I can find it later. Oh, and look what I did. I just ran that with a selection, so guess what didn't work? Basically all we did is cut that thing. Alright, so I'm just going to make this clip 2, and we'll try it again after I clear my selection. Okay, so now we have new data set just inside the boundary. Now, this is going to make our zonal statistics calculation a little bit easier as well. So anyway, that does save us a step. But we have to go through and recalculate our lengths. I apologize that you can't see this. I'm just opening the attribute table. And I've got a length field. We don't know what the units are. I've got all sorts of length fields, actually. Segment length, shape length, shape length. So I'm going to not use that one because it's right protected. This one's free, so I'm going to use my capital shape length to recalculate my lengths. I could add a new field. I'm going to make it a geodesic calculation because I trust those the most. I don't have to think about what my projection is. And I'm going to calculate it in meters. So now I know. And I'm watching to see if this changes. Okay, so now I have a new shape length, and I'm going to run zonal statistics as a table. And we want each one of our watersheds to have a unique identifier so that we can get a length, a summarized length for each one of our watersheds. So our zones are the watersheds. And our zone field, we need to check that and make sure that it's unique. So again, I'm opening the attribute table for the watersheds this time. And it looks like we've got an FID that's unique. We have an object ID that is unique. And we could probably use our HUC 12 number, which is going to be the most specific. So I think we have several options for unique identifiers here. So let's go back into our zonal statistics tool. An object ID will work. Let's see here. Let's use our HUC 12 name, because we know that one will also be unique. HUC 12 name. And then we know what to call it. Okay, and then our input value raster is not going to help us because we're working with polylines. So we're actually going to use a tool called Summarize Within. And how would you know that? Same way I just figured it out. I just opened a tool that I thought would work and realized that it only works on rasters. And so how would I know Summarize Within? Well, I would go here and say ArcGIS Pro, zonal polylines. How about that? Let's just see what we come up with. So zonal statistics would give us, if we had a raster, the polyline would allow us to pull the slope for each line. But what if we want to summarize features within polygon? Because that's really what we want to do, right? We want a summary. So summarize points within polygons, summarize data inside polygons, summarize within. So that's how I would go through finding out which tool I'm actually supposed to be using. Mine was just me being a buffoon and forgetting. Okay, so we're going to go back in here. We've got summarize within. Our input polygons are our watersheds. The summary features are, let's make sure that I'm using the right one, our clip 2. Okay, clearly going to make sure I'm paying attention. All right, so our summary fields, we want to summarize the length, and it was the capital shape length, and we want a sum of the values in this field. I don't know what this does. Let's look at the I. Specifies whether attributes for the number of points are summarized. Each input polygon. Sure. Let's do it. And then the shape unit is kilometers. That doesn't make a whole lot of sense. Okay. Let's leave it. Let's leave our units matching what we had calculated them in. We could, I suppose, transform them, but let's just not. Okay. Okay, when that's completed, we get a new output, our new polygons, that should contain, again, I'm opening the attribute table, this should contain our summary for each one of the, so we've got a count of the number of lines, we've got the summarized length in meters, sum shape length, so this matches, which it should, so I think we just did duplicate math. But for each one of our 10 watersheds, which makes sense, this is another way we can check to make sure that we got out what we wanted to. This is our total length. Now, how could we test this? We could test it by going into one polygon. We could select the polylines within one polygon. Let's see if I can find one that's kind of isolated, or we can just do a select by location, but I can select these guys here, and then I can go over to my clip and I can choose to, whoopsies, nope, I'm going to go, okay. So I can select the polylines in one of these watersheds. I selected them in our clip 2. We should have, so we have 122 records. Does that make sense? We should see that these are all in the same, no, this doesn't make sense. Let's see here, we need, let's select it here. I'm going to start over. Let's just clear this out, clear this out, clear that out, clear our selection. Okay, and now I want to just use the, there we go, and we just want to select those polylines, and so let's figure out where they are. Okay. Okay, so it looks like we have some of those polylines are named and some are not, which makes sense because you'd have the main the main channel going through there. And then you'd have all the little tributaries, which wouldn't have names. Okay, that looks good. And now we could go into the statistics for our shape length and get a summary. So our selection sum is 86,262 meters, so about 86 kilometers. And then we can go to, so this is the left fork of the south fork of the Ogden River. That's handy. And we can go into our summarize within, open the attribute table, and go to our left fork of the south fork of the left fork, south fork, Ogden River, and go look at our sum. And hopefully it's 86 kilometers, which it is. So we've just verified that what we're seeing in our summarize within table is the correct length, summed length, for each one of our watersheds' total polyline length. And so, because this is a polygon, we can also get now our shape area for each polygon. And we could do that in square meters. Then we could divide them out and get total length per unit area to get a density of channels. So let's clear the selection here. And I'm going to use the shape area if it'll let me. Nope, it will not. So I may just have to add a field here. Area in meters squared. Okay, I'm going to save that. Close that. Calculate geometry. Make it geodesic. And meters squared. It doesn't really matter. It's a normalized value anyway. It's not going to matter. It's per unit area. Okay, and now we can add a field to do a field calculation where we're going to divide our sum of the length, our 82 or whatever, or 86 kilometers by the area of each watershed. And so I'm going to add a field and call it density. I'm a floataholic. Doesn't mean it's good practice. I just can't help it. It's what I do. And then go back to our summarize within and find that new field and do a field calculation, dividing our shape length sum okay, that divided by our new area. And then we should be able to sort this descending. And this guy is our winner for having the highest density of polylines or stream lengths given the area, our highest density. And that is, here's our Huck 12, the outlet of the East Fork Little Bear River Canyon. That's it.